For decades, the most brilliant minds in human history have been chasing a single, elegant mathematical equation that can explain everything in the universe. Albert Einstein spent the last 30 years of his life trying to find it, scribbling formulas on his deathbed in a desperate attempt to unite the laws of the stars with the laws of the atom. He failed. Since then, thousands of physicists have taken up the mantle, working in the shadow of this unfinished masterpiece. We call it the grand unified theory or the theory of everything. It is the ultimate goal of science, a single framework that proves that all the complexity of our world, from the swirling of galaxies to the beating of a human heart, is actually the result of one single fundamental law. To find it would be to finally read the mind of God, as Stephen Hawking once put it. But as we peel back the layers of reality, we find that the universe is keeping its secrets well guarded, hidden behind a wall where our two greatest theories of physics refuse to speak to one another. The tragedy of modern physics is that we have two incredibly successful rulebooks for reality, but they are completely incompatible. On one side, we have general relativity Einstein's masterpiece. This is the physics of the very large. It describes gravity, space, and time. It is a smooth, beautiful theory that views space as a flexible fabric curved by the weight of stars and planets. It predicts the orbits of the planets, the existence of black holes, and the expansion of the universe with staggering precision. On the other side, we have quantum mechanics the physics of the very small. This is the world of subatomic particles, where things are pixelated and chaotic. In this realm, particles can be in two places at once, and nothing is certain until it is measured. Both theories are undeniably correct in their own domains. Without general relativity, your GPS wouldn't work. Without quantum mechanics, the computer or phone you are using right now would not exist. But when you try to use them together to explain something that is both very heavy and very small, like the center of a black hole or the very first microsecond of the Big Bang, the math breaks. The equations begin to spit out infinities, which is the universe's way of saying, your math is wrong. The search for a grand unified theory is the attempt to find a bridge across this divide, a way to unite the smooth curves of Einstein with the jittery particles of the quantum world. To build this bridge, physicists must find a way to unite the four fundamental forces that govern everything we see. The first is gravity, the oldest and most familiar. It is the force that keeps your feet on the ground and the moon in orbit. Ironically, while it is the most visible on a cosmic scale, it is actually the weakest of the four forces. The second is electromagnetism, the force of light, electricity, and the glue that holds atoms together. It is the reason you don't fall through your chair. The electrons in your body are repelling the electrons in the chair with incredible strength. Then we have the two forces that live only inside the atom. The strong nuclear force, is the most powerful force in existence. It acts like a cosmic superglue, binding quarks together to form protons and neutrons. Without it, the nuclei of atoms would instantly fly apart. Finally, there is the weak nuclear force, which is responsible for radioactive decay and the nuclear fusion that powers the sun. For decades, the goal has been to prove that these four distinct forces are actually just different shades of the same single force, behaving differently only because the universe has cooled down since the Big Bang. We have already succeeded in uniting two of these forces. In the 1960s, physicists proved that at extremely high temperatures, electromagnetism and the weak nuclear force merge into a single electroweak force. This was a massive triumph for science, proving that unification is not just a dream, but a physical reality. We then added the strong nuclear force to the mix to create the *** standard model of particle physics ***. This model is the most tested and successful theory in human history, describing 3 of the 4 forces with incredible accuracy. It predicted the existence of particles like the Higgs boson long before we actually found them in the Large Hadron Collider. But the standard model is incomplete. It has a massive, gaping hole. It completely leaves out gravity. Gravity refused to be quantized, while the other 3 forces are carried by particles, photons, gluons, and WZ bosons. We have never found a graviton, a particle of gravity. This is the wall we have hit. Gravity is the lonely force, the one that refuses to join the party. A true grand unified theory must find a way to bring gravity into the fold, proving that the curvature of space is somehow linked to the vibrations of subatomic particles. The most famous and controversial attempt to solve this is ** string theory ***. For decades, string theory has been the only game in town for many theoretical physicists. The idea is as beautiful as it is strange. It suggests that if you were to zoom in deep enough on a quark or an electron, you wouldn't find a point-like particle. Instead, you would find a tiny vibrating loop of energy, a string. Just as a violin string can produce different notes depending on how it vibrates, these cosmic strings produce different particles. One vibration creates an electron. Another creates a photon. And a specific elusive vibration creates a graviton. By replacing points with strings, the math that once resulted in infinities suddenly becomes smooth. String theory successfully unites gravity with the other 3 forces. But there's a catch several, actually. For string theory to work, the universe cannot have only 3 dimensions of space. It requires 10 or even 11 dimensions. Proponents argue that these extra dimensions are curled up so tightly that we can't see them, like the surface of a garden hose looks like a 1D line from a distance, but is actually a 2D cylinder up close. Despite its mathematical beauty, string theory has one major flaw. We have no way to prove it. The strings are so small that we would need a particle accelerator the size of a galaxy to see them. This has led some to call it philosophy rather than science. If string theory is the top-down approach, ** loop quantum gravity ** is the bottom-up challenger. While string theory tries to force everything into the language of particles, loop quantum gravity focuses on the fabric of space itself. It suggests that space is not a smooth, continuous background, but is instead made of tiny loops or nodes of gravitational field. In this view, space is quantized. If you were to zoom in on empty space, you would eventually see a chain-link fence of geometry. This theory doesn't need extra dimensions, and it treats space and time as something that emerges from these loops. It solves the problem of general relativity meeting quantum mechanics by making space itself a quantum object. It is a gritty, radical view of reality that suggests there is a smallest possible unit of distance and time. While it is less popular than string theory, it is gaining ground as we look for ways to test these ideas by observing the light from distant gamma-ray bursts or the echoes of the Big Bang. The reason we are so convinced a grand unified theory exists is because of the history of the universe. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. Scientists believe that in those first moments, all four forces were indeed one single, symmetric force. As the universe expanded and cooled, this symmetry broke. Gravity was the first to separate, followed by the strong force, and finally, the electroweak force split into electromagnetism and the weak force. When we search for a gut, we are essentially trying to reverse engineer the Big Bang. We are trying to find the mathematical conditions of that original, perfect symmetry. If we can find the equation that describes that superforce, we would understand exactly how the universe was turned on. We would see the blueprint of the cosmos at the moment of its creation. This is why we build massive machines like the Large Hadron Collider to recreate those high-energy conditions and catch a glimpse of the forces as they were before they drifted apart. What would a grand unified theory actually look like? Most physicists believe it will be surprisingly simple. There is a deep-seated belief in science that nature, at its most fundamental level, is elegant. We have seen this time and again. Maxwell united electricity and magnetism with four simple equations. Einstein explained gravity with a single short formula. A gut might be an equation no longer than an inch, something you could print on a t-shirt. But why should the universe be simple? Some argue that this is just a human bias. Perhaps the universe is actually a patchwork quilt of different laws that only look united from a distance. However, the history of discovery suggests otherwise. Every time we have looked deeper, we have found more unity, not less. We found that the heat of fire and the cold of ice are both just the movement of molecules. We found that the light from a candle and the X-rays from a star are both just electromagnetic waves. The search for a grand unified theory is the final step in this long journey towards simplicity. If we ever find the final theory, it would mark the end of a specific era of human thought. We would no longer be guessing at the rules of the game. We would have the rulebook in our hands. This raises profound questions. If everything is governed by a single deterministic equation, is there room for free will? Or are our thoughts and actions just the inevitable result of strings vibrating in 11 dimensions? Furthermore, a gut might reveal that our universe is just one of many. Some versions of string theory suggest a landscape of different possible universes, each with different laws of physics. Our unified theory might just be one of an infinite number of ways a universe can be built. This would be the ultimate Copernican revolution, moving from the realization that we aren't at the center of the solar system, to the realization that our entire universe is just one tiny bubble in a vast, infinite multiverse. The search for a grand unified theory is the greatest detective story ever told. We have the clues, the four forces, the particles, the expansion of space, but the pieces of the puzzle don't quite fit together. It is a challenge that pushes the human mind to its absolute limit, requiring us to imagine dimensions we cannot see and particles we cannot touch. It is a testament to our species that a group of primates on a small, rocky planet have even the capacity to ask these questions. As we move toward the middle of the 21st century, new technologies like quantum computers and next-generation space telescopes might finally provide the data we need. We might find supersymmetry, a predicted relationship between particles that would be a huge smoking gun for string theory. Or we might find that Einstein was right all along, and gravity has a secret relationship with the quantum vacuum that we haven't seen yet. In the end, even if we never find the God equation, the hunt itself is what matters. In trying to unite the forces of the universe, we have united the minds of humanity. We have built global collaborations, shared knowledge across borders, and reached a level of understanding that our ancestors would have considered divine. The universe is a vast, beautiful mystery, and the search for its unified truth is the light that guides our journey through the stars. We may be final second creatures on the cosmic calendar, but we are the only ones trying to read the whole book. And that, in itself, is the most grand unification of all.